Mark your calendars for November 18th, 2026. At exactly 2:16 in the morning Pacific time, something extraordinary is going to happen in deep space. Right at that exact second, NASA calculates that our farthest spacecraft, Voyager 1, will cross a boundary no human creation has ever reached. It will be exactly 1 light day from Earth. To fully grasp the scale of that achievement, consider the math. Voyager 1 has been traveling continuously for nearly 50 years. It is moving at roughly 38,000 miles per hour, never stopping, never slowing down. Half a century of constant flight, just to cover the distance that light travels in 24 hours. The light year remains a violent, massive physical distance, a gap that exposes the hard limits of current human engineering. This problem was first unlocked in 1676, when a Danish astronomer named Ole Romer made a strange observation. He noticed Jupiter's moon Io appeared out of sync with his math. A planetary model shows why. The discrepancy matched Earth's changing physical distance. Romer proved light travels. Moving to a linear scale, we see it crosses to our moon in about 1.3 seconds. When you let that beam of light travel continuously for 1 full year, it covers approximately 5.88 trillion miles. That 5.88 trillion miles is a single light year. That is the unit we are trying to cross. Your first instinct might be to ask why we don't just build a faster ship. We actually have. In late 2024, humanity's fastest creation, the Parker Solar Probe, reached a peak speed of around 430,000 miles per hour. If you could launch a spacecraft in a straight line at that top speed, it would drastically cut down the trip. Instead of the 18,000 years it would take Voyager, Parker's speed would let you cross a full light year in about 1,500 years. But there is a mechanical catch. The Parker Solar Probe achieves those incredible speeds because it's locked in a tight gravity loop around the Sun. It uses the Sun's enormous mass to slingshot itself forward. It isn't heading to another star, and its speed is useless for interstellar travel. Moving away from the Sun's gravitational help, Voyager's agonizingly slow pace is our true interstellar reality. We are currently facing an 18,000-year barrier just to cover 1 single light year. So if gravity assists won't get us to another star, why can't we simply build a new spacecraft with engines capable of going faster in a straight line? The answer lies in one of the most stubborn facts in physics, the rocket equation. This balance scale model illustrates the core problem. To make a ship go faster, you need to burn more fuel. But fuel has mass. To carry that extra fuel, your ship becomes heavier. To lift that new, heavier mass, you have to add even more fuel. The relationship grows exponentially, and the math turns brutal very quickly. This chart shows what happens when we try to push those limits. If you attempt to accelerate a conventional spacecraft to just 1% of the speed of light, the required fuel-to-mass ratio completely dwarfs the spacecraft itself. It becomes a towering mountain of propellant for a tiny sliver of payload, making the engineering essentially impossible. Even if you magically solved the fuel problem, you immediately face a second one. You can't just coast into a new star system. If you arrive moving at 1% of the speed of light, you will blindly shoot past your target in a matter of hours. To slow down and stop your spacecraft, you have to burn an exact matching amount of fuel in reverse. The limitations we face are baked directly into conventional physics. Our current mathematical models simply do not allow us to climb over this wall. To make matters worse, we haven't even properly left our own neighborhood. The solar system doesn't end neatly after Neptune. At an enormous distance sits the Oort Cloud, a vast outer sphere of icy comets and debris that marks the true boundary of the Sun's gravitational influence. This spatial map shows our solar system scaling outward. As the known planets shrink down to a single dot, the Oort Cloud reveals itself as a massive outer sphere. Estimates suggest this debris field extends outward to potentially 2 full light years away from the Sun. Traveling 1 full light year would still leave humanity deep inside our own solar system's outer envelope. We are staring at these impossible distances, and we have barely left the driveway. That reality sets a daunting stage for our actual interstellar ambitions. The nearest star to our Sun, Proxima Centauri, sits 4.2 light-years away. At our current top speeds, it would take roughly 73,000 years to arrive there. 1,000 human generations would live and die on a ship before it ever reached its target. Nobody alive today would be there to see it. Confronting these numbers forces a shift in how we view ourselves. When the astronomer Carl Sagan looked at the Voyager mission, he recognized that these overwhelming distances redefine our place in the universe. He famously called Earth a pale blue dot. He pointed out that every human who ever lived, every inventor and explorer in the history of our species, lived out their entire lives on a microscopic speck of dust suspended in a vast, dark cosmic void. The massive distance of a light year ultimately acts as a physical cage. It is a stark, absolute measure of the gap between what our current technology is capable of building and the distant worlds we want to reach. But Voyager 1 is still out there right now. As we speak, it is blindly covering 900,000 miles of empty space every single day. Knowing that these interstellar distances are currently impossible to cross, the natural question to ask is whether we should stop trying altogether. Tossing these machines into the cosmic ocean, knowing we will never live to see them arrive, is an act of ultimate defiance against our physical limits. We cannot cross a light year. Not yet. But our relentless, stubborn determination to finally figure out how is exactly what makes us who we are.